Hello everyone. Today we'll be talking about how the universe behaves at its smallest of scales. But what I hope you understand from it is truly nothing. On December 2004, a lecture was given by Frank Wilczek. In it, he emphasized that the mass of the protons and the neutrons that makes up the atom comes from about 90% of empty space, or from nothing. Well, that is the nothing that we'll be talking about today. To understand this further, let's go to the year 1907, where Einstein is celebrating his newly discovered theory of special relativity and decides to take on another challenge. And he decides to take the biggest villain of all theories, gravity. Well, it sucks. I know, it pulls things. At the time, almost all the physics community were convinced that gravity is complete, and it's well described by the well-known classical gravity presented by Sir Isaac Newton. But little did Newton know, although his theory was capable of describing the motion of the stars and the motion of the moon, the motion of rockets flying to the moon, Newton didn't know actually why gravity works. So, for example, why is the sun, that is millions of miles away, is capable of describing the motion, is capable of affecting the motion of Earth, that is along that distance? This was the task that Einstein set to explain. Einstein says that the medium that transmits gravity is the space-time. He continued saying that if we had a space, then this space is flat and unchanging and calm, much like this picture, if there is no matter or mass present in it. However, when there is a mass present in it, such as the Earth or the Sun, this space encounters some wiggling and warping and bending due to the effect of mass on it. And the more the mass, the more the warping, and then the more the warping, the more the force of gravity. Einstein continues saying that if we had, for example, Earth, then Earth warps the space around itself and creates a valley so that moon can circulate in orbit around Earth. The same is true for the motion of the Earth around the Sun. Earth is forced in orbit due to the mass of the Sun and the warp of the space-time around the Sun. Now, this is true for all the matters and all the galaxies and the stars in the universe. Einstein, accepting this fact that the gravity is a warp of space-time and that the universe is static, as all scientists believe it to be in 1907, he devised a picture of the universe. This is the equations he came up with. Little did Einstein know, his equations came describing a universe that is expanding and unchanging. But Einstein, as his predecessors, believed in a universe that is static, unchanging. These equations came describing a universe that is dynamic, changing and expanding. Well, Einstein said, let me stabilize this picture by introducing a term, and he called it the cosmological constant. We ask, what is a cosmological constant? Well, to understand this, we ask another question. Why is the universe big? The universe is big and is getting bigger and bigger at a faster and faster rates. The cosmological constant is the driving force that pushes the universe. Einstein introduced it, as we could see here on the left-hand side, as a constant in the geometry of space-time. However, if we decided to move the cosmological constant to the right-hand side, now it represents an entirely different term. It comes from the energy and the momentum of the universe. We ask again, what could produce such a term? Well, I, as much as many other physicists, believe that nothing could produce such a term but nothing. Well, is this the energy of nothing? If so, then what is the energy of nothing? Well, to answer this question, we embark on describing the universe on its grandest of scales. For example, ordinary matter in the universe, matter like me, like you, galaxies, stars, atoms, and eventually us humans, account for about less than 5% of the whole mass of the universe. 24% is dark energy, the stuff that pulls galaxies together, and 71% is dark matter, is the stuff that pushes the universe together, and it is energy of nothing, as Einstein introduced it in his cosmological constant. The cosmological constant is probably the most driving force that pushes the universe apart, and we don't know much about it. About 95% of the universe is invisible, and we don't know what produced this 95%, but we have a theory. We know that there is something that is pushing the universe apart, and we call it dark energy. Well, if so, then what do we know? Dark energy, the stuff that pushes the universe apart, causes the universe to accelerate in its expansion. And what do we mean then? We all know that the universe is expanding. Even children watching cartoons would know that the universe is expanding. But it wasn't until 6 years ago where 3 physicists, 3 astronomers won the Nobel Prize in physics that we came to know that the universe is not only expanding, but it also accelerates in its expansion. Well, and we don't know much about it. Well, the cosmological constant acts up as if you are driving a sports car and you are accelerating from 0 to 100 with a very high accelerated motion. The cosmological constant is the same thing as the cushion pushes on your back from the driving sports car and pushing your back due to the accelerated motion. The cosmological constant acts up in the very same way in pushing the universe apart and accelerating it in its expansion. Now, to understand this even further, let's dig the atom and go further to find that is made of protons and neutrons. Let's dig even further to find that is made of quarks. Well, Frank Wilczek, as I mentioned earlier, says that 90% of the mass of the quarks and the protons and eventually everything that you see in the universe comes from about 90% of nothing. And Professor Derek Lineweber provides us with a very nice simulation of the space in between these quarks, and this is vacuum. The energy lumps you see are called quantum field fluctuations, or simply gluon quark field fluctuations, as physicists call them. This is the true energy of nothing. Where you see the red spots, this is the high energy concentration of nothing, and the energy goes low as colors grading goes to yellow and blue, as we can see from the video. Now, what I'm trying to tell you is that vacuum is filled with stuffs, and there is no zero-state energy. And no matter how hard you try sucking things from vacuum, how hard you try, you would never, ever get the number 0, no matter how hard you try. Nothing. To make it clearer, let's imagine a travel bag. Everybody has had his travel bags with them. Well, let's imagine this travel bag that never gets emptied. As much as you take your clothes, you take your shoes off the back and you try to empty it, you still have more shoes or more shirts left so that you could empty. Well, this leaves us with a very unsettling picture. And even if we could get rid of these fluctuations that you saw in the video, still, this would open up another level of nothingness, where a variety of quantum fields and quantum fluctuations could pop into our universe and then fades away again. And much like this picture, leaving us with the analogy that the universe is far from being empty, and the nothingness energy is far from being nothing. Well, Henry Casimir gives us another picture of the universe. He says that nothing is filled with virtual particles, much like these, that comes in and out of existence each second. He also devised an experiment to test for these extra, virtual particles. He described an experiment with 2 plates separated by vacuum, and since that these virtual particles comes in and out of existence with a variety of sizes, then bigger particles wouldn't fit inside these two plates, resulting in more force outside the plates than the force inside the plates, which in its turn resulting in pushing the plates together. The experiment was done in 1997. It came to confirm that the universe is filled with this soup of bubbling virtual particles that comes in and out of existence. Now, let's imagine that these particles are small enough, right? We said earlier, as human beings, we experience 3 dimensions of space, such as the width, the height, and the length. Well, how could there be more dimensions? We said earlier that space could warp, bend, and curve, and contract. If we were to imagine one of the dimensions of the space to contract to a size lesser than the size of an electron, then this space would be very difficult for us humans to feel or see. But if we were to look close enough, then the space, that tiny space and that hidden dimension might eventually pop out. To take this even further for imagination, let's imagine a person walking on a rope, much like this picture. While this person could encounter only going backward and forward, an ant could go backward, forward, and go around the rope in what appears to be a curled up extra dimensions. As humans, we don't feel these microscopic extra dimensions or hidden dimensions because they're very tiny and small, but the virtual particles predicted by Henrik Casimir do. And these hidden dimensions that we said about earlier could be gateways bringing these hidden virtual particles into existence and then taking them out of existence again. As a physicist, I work in a field called quantum gravity. It predicts the existence of hidden dimensions. And these hidden dimensions, as we said earlier, could be portals to these particles. Well, as a physicist, I work in these hidden dimensions, and we notice that looking at these hidden dimensions is not enough. We need to test for these hidden dimensions. These hidden dimensions can be only seen if we try to see particles that exist only if these hidden dimensions exist. Well, how to test for these hidden dimensions? We accelerate the protons, 2 protons, to speeds near that of light and then smashing them together, resulting in a very high collision of a soup of particles. And this could be achieved through the Large Hadron Collider at CERN, which we could do hopefully in the near future. Well, nothing remains a very, very wide field. And one day we might be able to harness the energy of nothing and use it as free energy. But until that day, I believe, as much as many other physicists, that the best way to do it is to test for hidden dimensions. And if hidden dimensions are real, then virtual particles are real, and the universe is a key element of these hidden dimensions. Thank you.